Solving network problems using the power of duality theory. Abstract. Every day a large number of problems are studied and analyzed where modeling in the form of networks is a way of being more efficient in the search for efficient results for companies, organizations, associations, and even in problems of particular interest. At each moment gradually the number of study requirements of this type of case are becoming more frequent. This research document tries to show an alternative way of finding a solution to problems that can be very complicated, since they can exponentially increase the modeling as a whole of equations and feasible spaces. Hence the importance of remembering interesting linear programming algorithms as a source of inspiration for the state of the art that allows it to be viewed by researchers as a useful tool in large-scale network problems. Sometimes small prototypes can provide solutions of powerful in a simple way and without a high cost of implementation, where creativity is the way to find search solutions. Keywords: duality, complementary / network. Introduction. The problem originally formulated is known as primal, while its closely related counterpart is known as dual. The relationships are such that each is the dual of the other, and finding the optimal solution for one implies immediately finding the optimal solution for the other. Operations research aims to determine the best optimal course of action for a decision problem with limited resource constraints, applying mathematical techniques to represent by means of a model and analyze decision problems. Taha A. Hamdi, Prentice Hall, 1998. Operations research. A typical application of the dual simplex method is in solving problems with an objective function of minimization, with restrictions of the type greater or equal and where the decision variables are greater than or equal to 0. The duality theory establishes that a dual linear programming problem originates directly from the original model called the primal problem. The two are closely related, so that the optimal solution of one of them provides the optimal solution of the other. The dual problem could save a considerable number of calculations, particularly when the primary problem has many restrictions and few variables, which will involve a large number of calculations for their resolution by the simplex method. Another advantage of the existence of the dual program is the possibility of reducing the computational effort when solving certain linear programming models. It allows solving linear programming problems more quickly and easily. Networks. In a linear programming problem, a set of nodes that are associated with information such as cities, flows, distances, capacities, etc. can be represented, in which different types of solutions can be sought, such as minimizing costs, times, distances, or maximizing yields, profits, or capacities. Each node would be an equation in the set of the linear programming problem, in which the function the objective will be proposed with the same information provided in the problem in any of its two directions to optimize. It is essential to observe the importance of duality theory to minimize the number of equations. Trying to find a feasible solution in time polynomial, the efficiency of the dual problem is significant to establish itself as a potential alternative of systematized efficiency in a global approach to competitiveness, where the state of the art is gradually modeled, covering the different combinations and alternatives through which the silhouette moves towards the search for the optimal solution. The amount of real-world information that can be modeled as the network of networks is infinite, and with them the transcendent potential to accelerate solutions in real time. Complementary / theory. Often, linear program constraints are inequalities. This means that they do not necessarily have to be fulfilled as equalities, so there may be a difference between the values of the left and right terms. In PL terms, this difference is the slack. Conceptually, slack is the amount of idle resources, raw materials, financing, etc. available, but not used. Zero slack constraints are said to be active because they actively constrain the solution. Those that have positive slack are said inactive. In the complementary slack theorem, it seeks to guarantee that if the slack of a constraint takes a value other than 0, the corresponding shadow price will be equal to 0. If a shadow price takes a value other than 0, the corresponding slack will take the value 0. The inverse is not necessarily true. Additionally, it allows us to find the optimal solution of the dual problem when we know the optimal solution of the primal problem, and vice versa. through the resolution of a system of equations made up of the decision variables, primal and dual, and the restrictions, of the primal and dual model. The importance of this theorem is that it facilitates the resolution of the linear optimization models, allowing whoever solves them to find the simplest model to approach, from the algorithmic point of view, given that in any case they will be able to obtain the results of the associated equivalent model, be this the primal model. Network models and the complementary slack theorem. Network models are a necessity to implement real-life cases because a large number of problems can be modeled as networks using the linear programming as a solution tool. However, one of the limitations of mathematical programming problems is the explosion of equations when the models are programmed, since software is required to work to solve large-scale models. This is where the duality theory and the complementary slack theorem are powerful helpers for reaching solutions in real time. In the linear program document, Huerta, FZ, and Lara, RGL, 2015. Comparison of alternative solutions in linear programming modeling using the dual simplex method and duality method from primal problem, establishing implementation through the simplex methodology, says many real-life problems can be treated using the dual simplex algorithm, where an initial optimality to the actual feasibility of resources and goals can be adjusted with the methodologies presented in this investigation is determined. The strong relationship between the primal and dual models can be appreciated, from which the complementary slack theorem is derived as a powerful solver for solving network problems, since it minimizes the number of equations and facilitates the programming of models from the computational perspective. The modeling that can be obtained when the state-of-the-art is glimpsed from the edge of abstraction to execution in real time is truly splendid. Without a doubt, working using duality and the complementary slack theorem will provide a way of more practical management for administrators to easily visualize the depth and triadduction of each equation of the models that are represented, providing valuable information for decision-making and for the construction of process re-engineering to the operation models, where information such as time, money, capacity, efficiency, distance, etc. flows. In these times where efficient results are required in a short time, the duality theory is basic. Not using it is not only a waste but the loss of optimizing processes that in network models are configured to explain what happens in them and forecast future scenarios that improve the positioning of organizations and companies. When we can know what should be done to improve current productive actions, we are able to substantially increase profitability or minimize losses, concepts widely linked to operations research. Development of algorithms and software used. Chinese postman problem, CPP. Establishment. In 1962, the mathematician named Quan Macao was interested in how postal personnel could deliver letters on a certain number of streets in such a way that the total distance walked by the postman was as short as possible. The CPP is one of the classic problems in discrete mathematics. It is also a problem equivalent to that of the traveling agent, TSP, and is posed in the following terms: a postman must travel a certain number of streets in a city, each one at least once, and deliver the mail to later return to their office of origin. Eulerian Cycle. It is intended to find a route for the postman that allows minimizing the total distance traveled. If the network has an Eulerian cycle, it is clear that this will be the solution to the problem in another way. Surely some vertex is of an odd degree, which will cause routes through that edge, S, more than once. Recall that an Eulerian cycle is the cycle that goes through all the nodes only once and goes through each edge exactly once. The steps to solve this problem are summarized in the following sections. Step 1. Identify nodes with odd flow considering the arcs that relate to them. Step 2. These nodes should appear considering all possible pairs. Step 3. Find the smallest distance between each pair of odd nodes. Step 4. Choose the set of odd nodes that includes an even node and select the path with the minimum total distance. This even node is added to the sum of all the arcs between odd nodes to give the shortest distance to traverse the network and return to the original starting point. Example implementation. Solve the following problem in the delivery of couriers from the telebachillerato system in Michoacán, Mexico, to different work centers applying the CCP algorithm for the following offices. the lines represent the relationship between the dependencies and a number is also shown which is the length of the distances. You can see that the position of the post office, origin, does not affect the solution. Table 1. Odd and even. Nodes in the network. Step 2. Nodes and name. Relation between work centers. Distances in meters.